Hello everyone, welcome to the video lecture series on advanced separation process. Myself, Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJ Institute of Engineering and Technology. So let's continue with the chapter number 2, which is a membrane separation process. And in this lecture, we are going to discuss about various other methods of characterization of membrane. In previous lecture, discussed about various microscopic methods for characterization of membrane such as SCM, TEM and AFM. SCM, which means scanning electron microscopy, TEM, which means transition electron microscopy, and AFM, which means atomic force microscopy, and discuss about difference between scanning electron microscopy and transmission electron microscopy, and also discuss about difference between scanning electron microscopy and atomic force microscopy. Now in this lecture, we are going to discuss about various methods for characterization of membrane using membrane porometry and performance test. In this method, we are going to use membrane filtration setup and various other equipment such as a bubble point, then mercury intrusion, gas absorption and barometry, which use for the information on pore structure, where membrane filtration setup used for the find out permeability, rejection and pore size distribution. So let's first discuss about performance test for characterization of membrane. But before going to understand performance test, let's understand a basic fundamental definition such as a transmembrane pressure, which is useful to find out permeability, rejection and various factors. Transmembrane pressure is defined as a difference in pressure between two sides of membrane. It is a valuable measurement because it describes how much force is needed to push the water or any liquid or any solvent to be filtered, such as a feed throughout the membrane. So let's consider this is a one membrane setup where feed is going from this side. So basically transmembrane pressure, which means difference between the pressure of feed plus pressure of outlet divided by 2 minus pressure of permeate pressure, which means pressure by this side. So this equation describes how we can find transmembrane pressure. Transmembrane pressure, which means delta P is equal to input pressure plus output pressure divided by 2 minus permeate pressure. Input pressure, which means pressure of feed, then output pressure, which means pressure of the retentant or effluent, or can say that rejected, divided by 2 minus permeate pressure, which means pressure due to the permeate or pressure on permeate side. So using this equation, we can find the transmembrane pressure. The flow rate through the membrane or filter is measured at single transmembrane pressure, a pore length and porosity, and overall membrane porosity must be assumed or measured by the some other means. All the flow is assumed to go through a single size pore. So using this membrane filtration setup, we can find the permeability, flow rate and various resistance during the membrane separation process. So using this membrane setup, we can find the various performance test parameters such as permeability, retentant and various resistance during the membrane separation process. To find out permeability, we can collect the permeate in some vessel and measure the rate of permeation in some period of time. By using this method, we can calculate permeation for this membrane separation setup. Similarly, we can also collect retentant with some period of time, and using equation can calculate how much amount of retentant rejected by this membrane separation process. So this is all about the performance test. Now let's discuss about next method, which is a bubble pressure, or can say that bubble point method. Pore size of microfiltration membrane can be determined by bubble point pressure test. Using Cantor equation, we can calculate bubble pressure, or can say that bubble point pressure. So using this Cantor equation, we can calculate the bubble point pressure P is equal to 4K sigma cos theta upon D, where P is the bubble point pressure, D is the pore diameter, capital K which is a shape correction factor, theta which is a liquid solid contact angle, and sigma is the surface tension of that particular liquid. So using this theta value we can calculate the bubble point pressure. The above equation show that liquid will be pushed out of large pores of the sample at the lowest pressure, and increased pressure smaller pores of sample will be emptied at higher pressure. Because of large pores in a membrane is smaller than the smallest pores of interest in sample, the gas pressure required to empty the pores of the sample cannot remove the liquid from pores of membrane and permeate gas to pass through the membrane. This principle described in this figure. The membrane or filter is filled with the wetting liquid and gas separation is applied and increased. The membrane or filter is filled with wetting liquid and gas pressure is applied and increased. The differential pressure is necessary for the bubble of gas to displace the liquid filling the pore using the pore diameter and assumptions of circular cylindrical pores. The surface tension for the liquid and gas and contact angle for the liquid, gas and membrane material are required to calculate this. Bubble, which represent the gas penetration, can be determined by visually or electronic flow sensor. Mostly, electronic flow sensors are preferable for the measuring bubble count. As the pressure is increased, small diameter pores are empty by measuring the total volume of gas as a function of differential pressure. A pore size distribution can be obtained. This method is a subject to a many measurement uncertainty and will often underpredict the size of the largest pore. This is only strictly applicable when pores is much higher than the solvent molecule. Secondly, the method assumes complete the weighting of pores within the liquid. Third, it based on assumptions that pores are cylindrical and perpendicular to the surface. It is not known what is the effect of the geometry and shape factor. Improved equipment design and use of empirical correction factor can be decrease the measurement uncertainty. Typically used for the material with pores greater than 0.15 micrometer due to the transmembrane pressure required to displace liquid from smaller pores. So this is all about the bubble point pressure. Now let's discuss next method, which is a mercury porometry. For some membrane such as a ceramic or inorganic membrane, the mercury interaction test can be used. Mercury is a non-wetting fluid at room temperature for most porous material of technological interest. So using this formula we can calculate the mercury pressure, where P is the pressure, D is the pore diameter, or can say that dP, which means pore diameter, theta which is the liquid solid contact angle, and sigma which is the surface tension. So using this formula we can calculate pressure or pore diameter by gradually increase in pressure applied to a porous sample immersed in mercury bath and monitor the increasement volume of mercury intruded for each new applied pressure. The pore size distribution of sample can be estimated in terms of volume of the pores intruded for the given diameter. Of course, using the above equation to relate the intrusion pressure P and pore diameter D, assume the pore have circular cross section. Moreover, the surface tension of mercury is a 485 dyne per centimeter. Hence, high pressure need to be used that may be compress the membrane and distort the pore mouth opening. A further disadvantage is that membrane becomes dry. So using this instrument can calculate the pore diameter using mercury porometry. Our specimen, or can say that membrane sample, is placed here this in this holder. We can apply the mercury from this side and create the vacuum at this section using this vacuum pump. By using this vacuum pump, this mercury will be absorbed in the membrane and we can calculate pore diameter using this graph. So using intrusion, extrusion and reintrusion, we can calculate the porometry or can say that pore diameter using Hg porometry equipment or method. So this is all about mercury porometry method. Now let us discuss about pulse porometry method. Pulse porometry is a useful and convenient technique for the determination of size distribution of activity pores in membrane in size of 1.5 nanometer to 100 nanometer. The membrane is clamped between two flowing gas streams. The permeate side of the membrane is swept by the inert gas such as nitrogen. The feed side of the membrane is swept by the mixture of inert gas, condensable vapor and probe gas. This is quantitatively measured in trace level such as O2. The process is shown in this figure. The partial pressure of the condensable vapor is rise and lower to the closed or open pores of different size, typically 0.01 to 0.025 nanometer. As pores are open, amount of O2 that diffuse into the permeate side stream will be increased in proportion to the number and size of open pores. The uncertainty in the pore size result can be membrane swelling, cylindrical pore model insufficiently, and experimental measurement uncertainty. Let us consider pore solid is contact with vapor at pressure P as the relative vapor pressure is gradually increased. First manometer layer is formed on a inner surface of pore. With increasing relative vapor pressure, a multimolecular absorbed layer formed followed by the capillary condensation of vapor within some of the pores causing pore blockage. So, in this method, first we are going to apply nitrogen and which is our feed side, and for second side we are going to apply air in which there is a O2. Now these both are go to the membrane assembly using a carrier of ethanol. From this membrane the O2 can only pass, and due to this O2 analyzer we can analyze the level of O2 and find out how much pore size distribution all over the membrane. So this is all about this method. So in this lecture discuss about the various method of characterization of membrane. So this is all about today's lecture. I am completing my lecture here. Thank you.